Presentation, model predictive control with event-driven operation, presented by Willy Wojsznis from Emerson At-A-Glance.
Good morning, everyone. I'll be continuing presentation on the topic which already Terry started in some way, topic on model predictive control with event-driven operation. In my presentation, I make short introduction. When we started this project, MPC with event-driven operation, we had specific challenges. It was not an abstract project. We had divided wall column, which Terry described at the research center, University of Texas, and the divided wall column was instrumented by wireless instrumentation. Then I described a little bit feature of predictive control, which will be used there, and solution, which will try to make it event-driven. Finally, we see test results and conclusions. A few words about corporation. Emerson Process Measurement is one of the divisions of Emerson Corporation. And that's a major area of activities measurement, which include Rosemont companies, Micromotion, Daniel, Roxer. Then operate and manage is second activity, which we belong to, is Delta V distributed control systems, AMS suite, Ovation, and that's the next area of activity is final control, Fisher and Bettis, and all of those activities, they cover functionality of any control application. So as far as our division, we provide primary Delta V, which is distributed control system with functionality including advanced control. Just to compare with traditional advanced control, which is in most system, and I don't know other than our, which is unique solution. In traditional solution, this advanced control is applied in added workstation. So we have distributed control system, which is controller itself. This is operator workstations, and to implement advanced control, usually is added workstation. This is normal solution. In our Emerson provides this in such way that we implemented advanced control on the controller level. It really gives us significant advantages as compared to other providers, because the whole environment, design environment, operation environment, is on the same level like normal measurement and PID simple loops. So those are advantages listed here. Our challenge was a divided wall column, which is, as Terry said, is in a sense two distillation columns which are in series connected. So it provides two binary distillation columns. So it provides three components, three products, A, B, and C, as opposed to traditional binary column, which provides A and B. And as a result of that design, we have energy saving, but at the same time, control is much more difficult than traditional distillation column. That was column itself. And that is a control strategy, which is for that ternary separation in, let's say, local control loops. Definitely, to achieve full advantage and what we experienced in our testing, we need to apply multivariable control, in that sense, model predictive control. MPC strategies include just selecting controlled variables, which in our case are 4 temperatures, and selecting manipulated variables, which are listed here. And tool we used, it was Delta V Predict, which is, as comes from previous note, it is embedded into a DCS controller. So what is easy here that, as I said, we may use the whole environment, design environment, like for PID. So MPC block in that case is just normal function block like any other block in control design. To design and install MPC, we need to go through certain stages. So first stage, what was shown is really design graphical configuration. That's next step. We need to test process to develop model. Model is inspected, analyzed, and then we may design controller or generate controller. Offline simulation testing, and finally we may go to online operation, including optimization. Why we using wireless for DWC? Definitely instrumentation cost is much lower, and not less important is flexibility. In any research project, no, not only this one, using wireless instrumentation has additional advantages because of possible reconfiguration of the system and maintenance and easy expansion, all those very important factors for research projects. Definitely, basic requirements for wireless control are similar like for wired control, to provide stability, achieve performance, and what is really very important, provide switchover to safe mode if wireless connection failed. This is essentially key requirement for control. To see on the solution, we need to a little bit explain how works current predictive control. What is important here, that predictive control has model, which is called CV prediction. CV means controlled variable or process output. So we will use the prediction or process model to embed or apply wireless control. Process model is just a state space approach, but state in our case is a predicted trajectory of process output. This is what is written here. Controller generated is based on criteria. This is the simplest shown here. Criteria is to minimize error on the process outputs relative to reference trajectories, to minimize manipulated variable move, and essentially there might be added some other criteria which I'll not discuss here for shortness of presentation. This essentially solution is really what will be manipulated variable move depending on error and model, which is here. So what is the why I'm showing here? So model usually just normally use update every time we got measurement here. We update model. What is modeled? We need to refer to real measurement, update model. When there is wireless, we use this model in such way that we don't update model. We use only internal model for the control, which is maybe better explain this diagram here. So model update, this is shown one of the outputs. This is future trajectory, let's say at current state. And model updates comes into three states. First is we shifting our plot to the left. It's time update. Next, we update on the implemented manipulated variables, which we adding step responses, summarize step responses which affect that output, which is here. And third, we just update based on current, we see what is prediction, how prediction differs from current measurement, and update that prediction based on difference. It is wireless measurement, and we don't have feedback from the field. We just don't perform this third step, because that third step, if there is any measurement, might be completely false. And that's what we need to implement in model predictive control. When we got this problem with wireless measurement, we kind of looked on retrospect on our model predictive control, and happened that there are some already mechanism in place which allows working in event-driven environment for our MPC design. What are event in MPC operation? The first event is really a failure of the measurement. Let's assume this is normal MPC operation, and at this point happen failure of the measurement. It means that measurement has status bad. So since MPC is complex control, we cannot switch it to manual or to local mode just immediately, because it will be significant disruption for the process. MPC should operate certain period of time based on model. So this is really when status of the measurement is bad, we're still operating. MPC is operating based on simulated process output. That is essentially one case when MPC has kind of inherent feature to operate based on external driven event. Another case I mentioned is lab measurement. Lab measurement are coming time intervals which are much larger than MPC scan, which is shown symbolically here. Like, for example, MPC scan might be 1 minute, and lab measurement is coming every 15 minutes. And we still need control that output which is measured by lab. So what we do, we provide similar mechanism, and when status of lab output is constant, we need operate based on simulated value. We cannot assume that our value is just constant over this time. We need to use simulated value of that lab measurement. So similar with wireless measurement, everything what we need to do, generate status for wireless measurement, that status of that measurement should be constant, except when a new value is transmitted, status should be good. And what we did, we added like status generation for analog input, which based on the principle described, which shown here. There is another settings in our design. These settings tell how long we may operate in simulated mode per MPC. Usually we may not assume that MPC may work larger than time to steady state. Time to steady state is a time when some change on the process input happens, and this change will bring, after some dynamic changes, bring process to a new steady state. So we have such feature in our controller. Now it's shown that this wireless operation might be treated in a similar way like lab measurement or failure. Essentially, lab measurement may be good analogy, that when there is new value transmitted, we take this value using the control, but in between those transmission, we use simulated value of the process. This is operator screen, which shows timer, which shows whenever new value is transmitted, it's set on full maximum value for simulated operation, which we set at the MPC configuration, and after it counts until new transmission is coming. So we need to be watchful that it doesn't go to zero, and just to testing whether we set properly maximum time for working in simulation. This timer is really helpful. Those are tests. We made few tests in simulation before entering in the field. As you see, what is really very interesting picture here. Those wireless measurements are here, so they are constant. And when you would use those measurements over a longer period of time, control will be not good. We need to use some simulated value in between. In reality, we use, just shown here, we use simulated values, and there are some small bumps here when we update new measurement. So this is essentially what we did in simulation. We explored stability of the MPC control. It was stable, and we explored that we really not losing too much performance as compared to wired control. So those performance shown here, it's really less than, on average, 5–10% for various scans. Those are summary of those results. Now we go to the real application. This is how we make configuration. As I showed, this is MPC's normal function block. We have all environment like for a classical control here. So it's shown a configuration procedure here. We performed automated test of that distillation column. Surprisingly went very well. Usually in the field, you are not sure that one test is good because you need to set test plan, and sometimes it's really the environment is such that you need to repeat testing. In our case, we developed model. Those are process output. In our cases were 4 temperatures, and we developed model after first test. Those are step responses. We may see here that we supposedly choose time to steady state a little bit short because doesn't show that step response go to steady state. But this was due to our, again, a little bit short time. We have access to this distillation, limited access to distillation column. And actually, this is model validation, which showed really good resemblance to real trends. That's model green, and blue are real temperatures. I don't go into more details. I'll show final results. We may say here that prior to MPC control was local control. When we switch on MPC operation, performance was much better. That was shown on slides which we show temperature here. It looks like quite steady. And this trend shows those bumps, which are really not bumps of real measurement. Those bumps are only of those wireless which coming to the controller, and they are not affect operation. It's just to see the principle of how wireless work in MPC. And those are results. On the left trends, we have local PID control, and on the right, we have MPC control. And you see what are variations achieved with local control and MPC control. For the top composition, this is for side. Again, you see significantly temperature much more stable here, and same for bottom. So in summary, performance achieved using wireless MPC outperforms PID control for the DWC. Step responses with wireless control showed only slightly lower performance. That's what we saw in simulation, because on real plant we just may observe only graphics. We didn't make calculation for performance in sense of AIE or least square error. And even we make significant changes in feed flow, we didn't observe any temperature changes. So temperature was really stable, what is important, very important for that, for any column, specifically for that, with difficult control. That is acknowledged. We acknowledge cooperation with Eastman and University of Texas. Essentially, we supported control for that research project. More information you may find on book, specifically Advanced Control Foundation, which has edition shops which you may access even without book.
Thank you very much.
Thank you.
We are a little bit out of time, but it's okay.
Yeah, thank you, and have successful the rest of the conference.
Bye.